All right. Hey, everybody. So today we're going to be talking about these little gizmos. There's a disease called diabetes, and it sucks. And a part of it is that the patients need to monitor their blood sugar levels in order to know how much insulin they need. So this sensor is a replacement for the blood test strips. And the way that it works is that it has a tiny black wire that you inject into your arm, and then this sits on your arm for 2 weeks, and your smartphone or a dedicated reader can then measure your blood glucose without having to prick a finger or actually bleed. So we decided to take these apart and understand how they worked. Both coming from the top down by reverse engineering the cellular phone applications that communicate with the device, and also from the bottom up by reverse engineering the hardware, dumping the firmware, reverse engineering that, and getting remote code execution so that we're able to change the firmware that runs inside of the tag. And many reasons why you might want to do this. Chief among them is extending the lifetime of the tag so that you can use it for more than the 14 days for which it's medically approved. And I hope you enjoy the tricks we come up with. So, all right. You go.
Yeah, well, so actually we have already been introduced. I will make it fine with malware, so this is not a use today. This is a real device. IoT, and then Travis, you have something to add on yourself?
Yeah, so I do embedded systems engineering and reverse engineering, and I drive Studebakers, which are the greatest American company in history and the only one in all of history from now or the far future to die an honest death. They stopped manufacturing them in the 1960s, but they're beautiful cars, and I suggest that you buy one if they're legal in your country.
So I'll just move this around. Go on.
Cool.
Are you done?
Yep.
With that one? Okay. So yeah, this is a slide to remind you how it is working. So these things actually have a very thin needle in the middle of it. You can come afterwards and have a look at them. So actually it is not measuring glucose in the blood, which is the most accurate measure, but it is measuring it in interstitial tissue. So also it hurts a little bit less to insert it that way. Both of us, we don't have diabetes. I nevertheless tried on me. So this is a picture of me with one of these things on just to try.
I was too scared.
So actually putting it on is okay. Removing it is extremely hard because there's a really very hard glue there to have it stick on you for 14 days. The thing we haven't mentioned there is that, well, apparently the stats say that diabetes affects up to 9% of the population worldwide. So I think we can reasonably say that some of you in this room do have diabetes. Some of you have maybe used this kind of stuff here. So at first, it comes with this, okay, assembled in 2 different parts. You've got, well, this one has been broken or opened. You've got on one side, you've got basically the sensor itself, and the other part is the electronics part. It is communicating through NFC, so this is where you have the NFC PCB in there. So you assemble that, basically, and then you put it onto yourself. And then you have another step to do, which is here, right? You've got a specific application on your smartphone, or you can use a dedicated reader for this. And you've got to activate it. Okay, so this is the period where actually the sensor gets calibrated. It needs to pick up your body temperature to get accurate measures for your glucose level. And so this takes a little bit of time. And after 60 minutes, it is normally accurate, and you can use it and see what's your current level. And after 14 days, well, you've got to remove it, it expires, and you've got to go and buy another one, right? The limit, 14 days, it depends on the country. In Europe, in Switzerland, I believe it is 14 days. In the US, it used to be 10 days. And, well, I think that in other countries, there are different limits, right? So what have we done with that? Well, of course, the first thing we did is to try and open it. So actually, we're not the first ones to do this, to open it. There were other videos there on YouTube with people trying to open this up and see what is inside. They found it pretty difficult to open it without hurting themselves. The trick there is to unclip this part there, which is the enzyme sensor part. Once you unclip this, then it pops up open more easily. Then you just put a blade in between here, and you kind of open it that way. And I managed to do it, so it's easy, right? And this is so a zoom on the sensor, the enzyme sensor itself. So here you've got the needle. As I said, it is very thin, less than 1 millimeter. It is covered with a semi-permeable membrane on which there is glucose oxidase, GOX, and this reacts with the glucose in the body. And the reaction creates an electrical signal, which is then sent, of course, across those 3 contacts there. And there it goes to you.
So, as you go beneath the enzyme sensor, you have the circuit board of the device. A few things to note. It's the laser pointer. So, up here... Nope.
Doesn't work?
So here in the top left, you see a Texas Instruments chip. This is the RF430 TAL152H. If you search for this part number, you'll find that it's not a publicly available chip, but that there is a publicly available chip called the RF430 FRL152H, which is very similar, though not identical. We'll get to the differences between them in a bit. You'll also see that there are test points next to the chip for JTAG. These test points are used in the factory to program the chip.
This works.
Cool. So these test points here are used to program the chip in the factory. This could have been a good way to dump the code out. It turned out not to work for us, and we'll get back to that in a bit. The other thing to note is that there's a ring around this circuit board of a wire that crosses 3 times. This is the near-field communication antenna that provides both power and signal to the chip. And then, even though it runs without the battery, there's a small battery here in order to make the readings more reliable. Like anything in the medical industry, it would be nice if the device could run without a battery, and it likely works rather well without the battery, which is optional. But they ship a battery anyways in order to make sure that the readings are as reliable as possible. Now, the RF430 FRL chip, the one that is publicly documented, data sheets are available for it. Example code is available for it. You can buy development kits for it. All of these things are available. It's just a slightly different chip than what ships in the commercial medical device that we're reverse engineering. The nifty thing about this chip is that it implements ISO 15693, which is the most modern type of near-field communications tag. Not all cellular phones can communicate with this protocol, but very many can. If you have a modern iPhone or a Google Pixel, they certainly support it. The other nifty thing about this, of particular interest for those who are making NFC tags, is that this chip uses ferroelectric RAM, called FRAM. FRAM is sort of like core memory, but modern. It takes very little power to read or write FRAM. It is very fast, almost as fast as SRAM. By comparison, flash memory takes a ton of power to write. And writing requires erasing an entire page. And that much power can't come over the near-field communication link. By using FRAM, you have non-volatile memory that is not erased when power goes away. And because it uses so little power, you can often run these devices without a battery. Now, the nice thing about having a publicly available chip that is related to the private chip that our device uses is that the pinout is documented in the public chip and happens to match almost exactly the commercial chip. So all of these pins that we see around the sides are accurate. And this allows us to know what the different pins do on the circuit board without having to guess. You can see here that the antenna connections come out through these two tuning capacitors. There's an analog to digital converter, a temperature sensor, a test pin, and then another analog to digital converter. The individual signal names of the JTAG port are documented. So we now know not only that those test pads are probably used for programming, but we know that they certainly are used for programming, and we know exactly what they do. So we wanted the firmware from this. We wanted to be able to read the code that is in our medical sensor in order to understand how its software works. So I bought this board from Texas Instruments, which is a development kit for the publicly available chip. The circuitry on this board is designed to convert the voltage so that the black device in the background, which is the Texas Instruments flash emulation tool for the MSP430. It allows that to connect to our chip and debug it. And when I connected this to the commercially available chip, it wasn't much trouble to get a working debugger. I had GDB running, I could read memory, I could write memory, I could set breakpoints. When I tried the same thing on our commercial chip, it didn't work. And we're still not quite sure why. So we had to find different tricks to dump the firmware. I got tired of using TI's board, mostly because certain pins, like TST1 and TST2, were not exposed on that board. So I designed my own, which I call the Good Tag. The hardware and the firmware for this went public on GitHub this morning. So you can now download this design, you can manufacture your own, you can read the source code to it. I have a slightly modernized revision with me, and this is pretty much the same as the TI board, except that it's got a prototyping area on the right, and it's thin enough to fit in a wallet. The other advantage of having these boards is that we can begin to write emulators. So as we're trying to understand how the commercial device works, we can write firmware that pretends to be the commercial device in order to log responses to different commands or in order to ensure that we understand the protocol of the device. By copying it well enough to confuse the real reader, we will then know that we understand it ourselves. Is this one you?
Yeah, I think so.
Cool.
So we said that we have those sensors which are readable using NFC. So basically, you can use any NFC reader that you have that supports ISO 15693, and it will work. The problem maybe for Linux, at least Linux people, is that many of the readers that we find cheap out there, such as NXP's PN 532, they do not support this specific NFC, right? Well, you've got to work out to find one. You can use Hydrabus. This is Hydrabus here with the extension for NFC. This one supports the right one. And otherwise, you can also use Proxmark. So this is what I have got here. This one, Proxmark, to read it as well. The other thing which is you can notice here is the sponge. So basically the sponge is replacing my arm. Okay. At some point I got tired with having a patch on myself, especially as it was totally useless in my case. So I decided to find a replacement. So you get a sponge, you pour hot water with sugar on it, and you get a glucose reading. Okay. And my colleagues find me very weird, but they are used to that, so that's okay. It supports the device plenty of standard NFC commands. You might know some of these: get inventory, read single block, write single block, read multiple blocks, things like that. For those commands, the first byte there is for flags, basically, and the second one is the command identifier. And then depending on the command, well, you have here various arguments. So we dumped them a few blocks which are available through NFC that way. And that is where actually I'm going to shorten very much our research. This took us lots of time. We did lots of tests, okay? What is the reading of the sensor when it hasn't started? What happens when it is being activated? What happens once you are reading this or that measures? What happens once it has expired? We also used several different applications. This one is the official application, but actually there are many other applications out there, open source. So we could have a look at their source code and see how they were discussing with the sensor. So it was quite useful there, and try to work out how all of this is working. And this is how we managed to understand the memory layout of the device. So basically what happens is that every minute the device gets a glucose measure, right? And this is a 6-byte record, which ends up in this table here. It piles up, and as you know, of course, on those chips, well, you don't have infinite space, right? So at some point, this table is going to be full, and this is where you start writing a history record. And then same thing, once you've written your history record, well, you can overwrite the trend records, and then in the end write a new history record. And when you've also filled the history records, well, this time it's completely full. You will start overwriting your different records. So at each time you have to store an index that tells you where you are currently working in that table. So you've got a trend index and a history index. After that, you also have a small portion of the memory which is storing the wear time, how long you have been wearing your patch. So this wear time is stored in minutes. It is 2 bytes. And you have also a little bit after that the sensor region. As I told you, there are differences depending on the countries where this is. I haven't said that, but this device, I think it's sold in over 45 countries, and there are already 1.5 million units of it sold. So it is really pretty much used worldwide. So this is where I try a live demo with my Proxmark, and it's not working that well. So we'll see if that works. So I'm going to show you how I read from that. So, yeah, it's behind the glass. I'll push your glass if...
oh, that's fine.
But it doesn't matter, right? And I didn't plug in the right one. I've got to plug in a high antenna one. It looks better. There. And, yeah, I told you it's not working very well.
Mm-hmm. It's a shame that we can't just buy a commercial off-the-shelf NFC adapter and then run Linux software on it. But it seems that all of the modern NFC chips are being sold for use in cell phones. And only the most bare minimal functionality is exposed in the working example for desktop operating systems. And then also all of the older chips, the ones that are supported by the publicly available NFC libraries, lack support for NFC Type 5, the ISO 15 standard that is used by this chip. So it becomes easier to communicate with these devices by a cellular phone or by custom hardware than it is by expecting anything off the shelf to work.
Okay, so, well, most of the time it ends up working. It's just the reader, the Proxmark reader, mine is clicking. It has been clicking for the last 2 days, so I thought it would probably work until today, but it's... there it is. Oh. Okay. So here, this is just the basic command telling it to use high frequency, and 15 is for ISO 15693. And we dump the memory. And here we are reading, well, not this one, because it's got to be very close to the antenna there.
Now, the memory that's being dumped here is the publicly available memory that contains the glucose records. This is not all the memory of the chip. Yeah. Specifically, it's lacking the mask ROM, which contains the permanent software of the chip, and it's lacking the SRAM, which contains the live variables that software is using.
And then, so once we dump everything that we've got available only through this part, through NFC, we wrote just, well, a small script to read and understand that the contents of the memory. So here we highlight with different colors, for instance, the trend index, the history index in that case. We've got then the trend records, history records. Here, the wear time, so it's 4400. You've got to turn it the other side. This means approximately 68 minutes it has been worn in this particular case. So that's a little bit over 1 hour. And the sensor region for this one was Europe, UK. We believe this is the region for that one. So that's pretty much how we began our reverse engineering for that one. And then that's for you.
All right. So I mentioned that during the demo that this publicly available region is not all of the memory of the chip. But luckily for us, it's still a very important part of the memory of the chip because there's more than just the glucose readings in here. This layout diagram shows the very end of memory. And the interrupt table at the bottom, that is the far end of the address space. That's a FFFF for the end of it. So when we first dump this and we look at it, we see at the very end that there's an interrupt table. This has a list of addresses where the chip will jump to when an interrupt is fired. This tells us where the chip goes in order to accept a new incoming packet, where to go when it's first powered up. Unfortunately, all of those addresses are inside of the mask ROM, which we don't yet have a copy of at this point in the research. So we want to get a copy of that mask ROM, and the way to do that is to understand what commands are available to us. So reading through this region, we find that there's a command table that uses AB as a magic number to mark where it begins and ends. And in the publicly available chip, there is a table with the exact same format, except it uses a different magic number. It's like BC. So we then know that the command table is a list of addresses and handler commands to add extra commands to the NFC protocol. So the slide a few back that showed the different commands that this chip supports by the standard is not the complete list of commands supported by the chip. Instead, we have an extra set of vendor proprietary commands. They begin with either A or E, and by reading this image, we're able to see that the E commands have been disabled, but that the A commands are still accessible. The easiest thing to do would be to overwrite this with our own commands, but we're not able to do that because the publicly available region of the chip is write protected. So while we can't go through and immediately change this, we do have a copy of a few of the commands, including A3. And A3 is my favorite command because it is a vendor proprietary command that allows me to read from a raw address. If I can call this command, I can dump all of the memory of the chip. And remember that this chip is a microcontroller. There is a complete computer in here with its own software, and that's the goal. Dumping that code and reading it allows us to understand everything that chip does, its entire protocol. So we know that the commands begin with A's. We start looking at the data sheets for similar chips, and we find that there are other chips that use vendor commands that begin with A. Unfortunately, these commands don't match what we see in the machine code for the available command in the FRAM. So, knowing that they're declared in this region, this FRAM toward the end, what we're trying to do is to grab the earlier FRAM, SRAM, and ROM regions. And then when we have that much of a dump, we can load it into IDA Pro or into Ghidra or Radara 2 and then figure out the behavior of the complete chip. The way that the chip works, both the publicly available one and the commercial medical one, is that the ROM contains a base program that defines almost all of the behavior of the chip. And then in SRAM, there's a table of function pointers, and those function pointers are changed to allow patching from the FRAM. So the bulk of the code is in the ROM, and a tiny bit is in the FRAM. The tiny bit includes the A3 raw read command, which I show here in Ghidra, the reverse engineering tool that the NSA published in February. On the left pane, I see the disassembly of the function. And then on the right pane, I see the C source code that has been decompiled from it. The nice thing about Ghidra is that it's able to decompile anything that it can disassemble, so that we can work at a higher level than the raw assembly language. Reading this, I could see that the function would check the vendor number, which is standard for any command handler. And then I see that it's calling something in that function table, which turned out to be a password check. And then I can see from the rest of the code that it takes a 16-bit address and an 8-bit count of words to return back. So I know everything necessary to call this function except for the password. It turns out that it takes a 4-byte password, a 2-byte raw address, and a 1-byte length. So how do I get the password? Well, there's more than one vendor proprietary command. A3 is the only one that I can read at this point, but I can guess at what the others might be. And I guessed that one of those others would initialize the sensor. This guess happened to be true. So I took the vendor's reading device, which you see on the right, and I connected it to the logic analyzer on the left. The cables are going to the SPI bus between the microcontroller in the reader and the TRF7970A chip that implements NFC. This is the equivalent of tapping like an old computer between the main unit and the modem by listening to the serial port. So this gives me a complete record of everything that goes on over the NFC connection, and I don't have to mess with capturing the signal over the air. I get absolutely accurate bytes, I write a Python script to parse them, and then I get my magic number. The password is presented as the device is initialized. So even though the A3 command, the raw read, is never used by the device in the field, I still get that same password as the A0 command is called to initialize the sensor. The password is not dead beef. but you can pretend. So now we know the custom commands. We know how to initialize the sensor. We know how to get its serial number. The info command doesn't require the password. It was the only one that we were able to call before figuring this out. I'm able to lock the device, perform a raw read, and I'm able to unlock the device. Unlock, the A4 command, turns out to be just as useful as the raw read command, because the unlock command unlocks the write protect and allows us to change the software on this device. So at this point, I got frustrated with typing in commands by hand. I wrote an Android app to automate dumping the device. So now I'm able to take any one of these sensors, tap it to my phone, and a few seconds later, I get a complete copy of everything interesting from memory. I then loop that back into Ghidra. And here, on the right side, you see the password checking function that we weren't able to read before. And on the left, the places that are blocked out, that is where the password exists within the mask ROM. At this point, I absolutely know that I have a complete dump of the device, that nothing is missing, and that I, with enough time, could figure out how everything works in the software of this device. This was a happy moment. There were other commands, as I mentioned. There's E0, E1, and E2. These were disabled by the time I got the device. You can see by the way the memory is set up that they used to be enabled. So I'm assuming that these are factory test commands that are used in the factory but never by the customers or after release. You can also see in older dumps that these weren't always disabled before they shipped out. It's possible that these commands were being used in the field and then a decision was made to turn them off. If at the same time they had disabled the A4 and A3 commands, then we would not have been able to get this far by these techniques. We would have had to succeed in unlocking the JTAG somehow.
Yeah. So about other commands, so we saw A3. The other thing is that Travis mentioned is that initially, when we wanted to write into the memory of the device, well, it would tell us that it was write protected. So the initial error is really explicit. The specified block is locked, and its content cannot be changed. And this is where the A4 command is extremely useful. It unlocks it, again, with our favorite password, deadbeef. And then you can write again in the FRAM. You can write parts in there. So what can you do with that? Well, of course, then it means that you can tamper the memory of the sensor, right? So we can virtually modify the firmware of the sensor and do anything else we would like to do with this device, right? There are a few limitations there that we saw, but you told me you might know how to overcome that. A few blocks like between 0 and 3 are not writable, and also block EF isn't writable at the very end of the FRAM. The other thing which might be interesting, right, is how about if we tamper the glucose records, and instead of saying that you have, 70 milligrams per deciliter, you have 20, something like that. Is that possible? At this point, today it is not, but we believe we are very close to that, because what happens is that those records are protected by a CRC. That's not a good cryptographic protection. But the fact is that, first, we are not exactly sure of the algorithm for the CRC. We have very good hints, but we're not entirely sure. And the other point is that we are not exactly sure yet where the CRC sits in the memory. So because of that, we are able to modify the records, but if we modify them, then the mobile application shouts that something is wrong. And
note that these are not particularly strong strongly enforced defenses. These are things that require development time, but not new techniques. So the blocks that are not writable externally, but they're still writable internally. When we flash new code to this device, that new code can add a raw write command that ignores the write protection settings. And similarly, the mask ROM itself has a command to check the CRC. So we can convert that code to set the CRC with development time.
Yeah. So we will get to it. So now there was a little bit of thinking about, well, is this a medical threat or not? So you've got to keep in mind several things at this point. First, of course, it requires proximity. Okay, it's NFC. So the attacker needs to be really close to the victim in that case. Also, of course, we reported this write issue to the vendor. It has been fixed in the models V2 of this sensor. They have started shipping in October 2018 in the US. I believe at least that in France and in Luxembourg, they haven't started shipping yet. So when you go in a pharmacy, you still get the old versions. I don't know for Switzerland. I haven't been shopping. So I don't know that. The other things also is that, well, we asked several diabetic friends, and all of them told us that, well, they usually had this condition for quite a couple of years, so they know how their body feels at this or that level. So if this is not consistent with the readings they get suspicious about it, they get another reading. If it's still not consistent, well, they will do a blood test, right? And the same thing, hospitals do blood tests for that. Okay. Finally, also the other thing, okay, this one is it's not injecting insulin, okay? It's just a sensor, so it just tells you how high your glucose level is. That's all. And then you decide if you want to inject insulin or not. So this meaning that, although it is extremely interesting for hacking, what we did, I believe, it is not really an attack that is that interesting for an attacker except in movies, right? Okay. It would be complicated to do something really interesting for an attacker here. There are much easier way to attack diabetic patients. We'll discuss that afterwards, directly on the smartphone. So the last thing we haven't discussed is that 14-day limit for the sensor, right? Why would it be possible to get it, I don't know, to work for 15 days, for 16 days? Obviously, that could be interesting in some particular cases. I'm taking aside here the medical reasons for it to have a limit. Of course, if you keep it on you for 30 days, I believe it's really going to start to itch or things like that. It wouldn't be medically reasonable. I'm only talking here about the technical part, of course. So what happens is here at this level here, you've got the mobile application and the Dalvik code of the mobile application. Then here you've got the native library inside the mobile application. This one is pretty much obfuscated. And then after that, you can also talk to the sensor itself. And all the communication then is through NFC. The first thing it does to see if the sensor has expired or not is first to grab the region on the sensor. It grabs it. And then what it does is it checks, is that sensor supported for this mobile application. So if you have a sensor which is for US and your application is for Europe, well, it's gonna say no, either get another sensor or get another application, but that doesn't match. With, if it is supported with that, well, it will get the correct limits, which are, the activation time, 1 hour in Europe, and, expiration, limit, 14 days in Europe. Then, it sends a command to read all blocks on the sensor between block 0 and block 2A. Here I'm talking about the NFC blocks at the end of the FRAM. Okay. And it retrieves all of this and sends it back to the mobile application. There, it bufferizes those blocks, and then asks a native library, is this okay, or has my sensor expired? If it is okay, it will then set an alarm, and in 14 days, the alarm will be triggered, and then it will do everything it has to do to mark the sensor as expired. So we thought about that and thought, well, okay, I don't know if you've noticed that the blocks are memorized here. So what if we don't actually send to the native library the real blocks, but fake blocks? And of course, I'm going to take blocks that I'm got from another sensor which hasn't expired yet. And we're going to send that to the native library. So the native library will be fooled. Indeed, it works. It is fooled, and it says, oh, right, okay, your sensor is fine. Go on and use it. Right. So this is what you see. You see in the end that, well, you can get some glucose reading there. I have a video for that. So this is not a live demo for this one because it's really a bit more complicated to set up. But there we go. So here I'm just showing you a sensor which has expired, just to show that it had expired and it's not working there. So it tells you, well, it's in French, but that you have to remove the sensor and to get another one. That's about this one. And then I am using again the same sensor, but this time I am going to use a hook using Frida. And instead of sending the normal blocks, I am going to send the blocks of that sensor I had, which hadn't expired. And then you're going to see the difference. Well, it tells you, okay, you can now use your sensor and scan. And we are going to scan. And it gives me a nice result, 88 milligrams. So it works. Actually, it is not reading off the body. Of course, it was, you can see it's totally detached. So that was probably the last measure, which was in the sensor, 88 milligrams here. The other thing that we managed to do here is that normally, so you see when you scan the sensor, it tells you, okay, this sensor is going to expire in normally 14 days. And here, notice, this one says 90 days. So, okay, we virtually managed to extend our sensors to be able to work over 90 days. So how did we do that? Well, same thing. When we are asking the native library goes and fetch the limits in the sensor, and it says, okay, this is a sensor for Europe, so you should have normally 14 days. 14 days is 100,000 here minutes. And then with Frida, you can hook this and say, okay, I'm saying, no, the limit is not going to be 14 days, but 90 days. There it is. And this works. And then the rest of the flow of the mobile application works. And this is where you get your 90 days there. And so, well, we are pretty done here. To wrap it up a little bit, what we can say is that it's a pretty nice design for this medical device here. I had personally looked into other IoT devices before that, and most of the time the design was really crappy gadgets with lots of security holes. It's not the case for this one. Of course, nothing is perfect. It did have, in that case, for instance, a vulnerability to be able to write in there. You also perhaps notice that, well, it is readable by anybody. So if you are in a packed bus and somebody is close to you and you have diabetes, well, they can read your measures and you won't have any warning of that. Okay? But still, the design is still nice, despite this thing. In terms of threats, so we said, well, it was mainly hacks, interesting hacks to be able to extend it. I don't know, to use it, for instance, if it's your child has diabetes and he's at school and you want to interact, to question the sensor remotely or things like that. If you want to do something a little bit more hackish with it, of course, beware what you're doing. It's might be important. But in terms of real cyber security, I feel that, however, the real threats here are more on the smartphone. It's going to be difficult to attack the sensor, as you may have seen. But it is far easier, unfortunately, to get a ransomware, for instance, on your smartphone. And if you have a ransomware on your smartphone, well, you won't be able to scan yourself any longer, which means that you have to go back to the manual way and get a blood test, which is, of course, a nuisance. Do you have anything else to add? I'm done on my side.
Yeah, I'd also like to mention that we're not just saying that this is like a pretty good product. We're saying that if we were diabetic, we would buy and use this despite the vulnerabilities that we found in it. At the same time, if we were dependent upon this technology, we would spend a lot more time reverse engineering it in order to know absolutely everything about it. Because you really ought to know as much as possible about the medicine and the technology that you use. We'd like to thank all of the diabetics who passed us sensors to reverse engineer and helped explain to us how these technologies are used day to day from like a first-hand patient perspective. We would also just like to quickly mention before questions that we have a number of these GoodTag NFC emulator cards. You can program these in C from your laptop. From your smartphone. So if you do Android development or if you do C development and you would like to mess with these, find me anywhere at the conference that is not this room immediately after the talk. And I'd be happy to share one with you. And with that, are there any questions? Yes.
Thank you. You said it stores the minutes in a 2-byte value. So a 2-byte value can keep at max like 60,000 minutes. Wouldn't that overflow after 1 or 2 months and reset the sensor basically?
Yeah, I tried it. I overflowed it that way, but my sensor was still marked expired before that. So the problem with it is that I only get the sensors from people who have diabetes, and they give it to me once it has expired. Right? I could buy occasionally 1 or 2 sensors on myself and do the tests, but then I only have 14 days to finish my research, and sometimes it's a bit short. Right. So in that case, once it is marked expired, it doesn't, you can't do anything about it any longer by just shifting the wear time.
All right. Thank you.
But I believe we will manage to overcome that, however.
We have code execution now, so we can change anything in memory we want.
Does it run Doom already?
It does not run Doom. There's enough room for NIM. Maybe I could add a blackjack game. Craps.
Are there any other questions?
Yes.
Wasn't too much of the memory readable at the first place? Does it make sense to have everything readable? Not everything, but the whole FSRAM.
So, yes, on the one hand, you would like to limit what's readable. On the other hand, the version 1 of this product, the one that's available here in Europe and that we used for this project, it's kind of nice that it's open because all of these third-party apps were able to be written to use the medical information off of the device. The second version does not present easily interpreted data. It looks scrambled. It might be encrypted. There's nothing in the view of that looks like code or an interrupt table, which is certainly going to slow us down in reverse engineering this new model. But I don't believe that it's a complete stop to reverse engineering. For example, the JTAG reverse engineering that we began earlier on that led to a dead end, that should work if we can make the chip reset itself as it does on the assembly line floor. So I believe that if we hold the test pins in a certain configuration as we reboot the chip, that the mask ROM will overwrite all of the FRAM and leave it in an open state for factory programming. It's also possible, because this is FRAM, a magnetic state is holding the bits of this chip. And the Curie point for the chip is coincidentally 430 degrees Celsius. So if we raise the chip to that point without burning the packaging, and then we put a strong magnetic field on the chip, we might be able to turn all of the bits to zeros or to ones to unlock it. So yes, hiding a bit of the FRAM would have slowed us down, but I don't think that it would completely stop attempts to reverse engineer the device.
Okay, thank you very much. And let's all thank the speakers.
Thank you.